So, guys, today, to wrap up the unit, we're going to talk about Le Chatelier's principle. But as has been the case throughout this unit, we get to have conversations now that we couldn't have had last year. The reason we get to have these conversations is because of the previous stuff we've talked about. You understand rate. You understand rate laws. You understand reaction orders. All the things that will be on Tuesday's test, by the way. Yeah, this is the end of the unit. So, guys, you know all of this stuff. And because you know all of this stuff, you can then understand Le Chatelier's principle in ways that you couldn't before. Now, all of this comes with a warning. Ready? The test that you just rewrote, you were all warned, and some of you disregarded the warning, but guys, you were all warned when you're talking about why things dissolve in other things. You don't get to say like dissolves like, because guys, atoms don't understand English. They don't get that. They dissolve because of all this interplay in forces and things like that. So when you're explaining, you don't get to say like dissolves like. Guys, similarly, relative to Le Chatelier's principle, you also don't get to say same side does the opposite, opposite side does the same. If you write that on your test, you may as well just put an X through it because it's going to be wrong. Okay? Guys, understand that we share these little, would that be a mnemonic? I don't even know if I know what that means, but let's pretend that's the right word. We'll ask Mr. Ellingford later. Guys, we share these little sayings so that we can use them in a predictive manner, but we don't use them when we're digging for explanations. So, with that said, guess what's about to come up on the screen? Same side does the opposite, opposite side does the same. Guys, you will never write that in homework and you will never write it on a test. So why do I share it with you? Because it allows you to do predictions, and then the explaining process has got to go down other avenues. So with that said, Le Chatelier's principle functionally says this, and you're all going to write it down. I'm not even going to mention it. Go ahead. So guys, Le Chatelier's principle says this. When you have a system at equilibrium, and when you stress that equilibrium, the equilibrium will respond by trying to undo the effects of whatever that stress-causing agent is. And guys, the problem with this definition is that it puts the equilibrium system in the position of making decisions, as if that equilibrium system is going, hey, I'm the Haber process, and you added nitrogen to me, and I'm going to turn it into NH3. Guys, you understand these systems are not sentient. They're not making choices. So while we can understand this idea of undoing stress, fundamentally, you've got to understand why this works. And it all relates back to reaction rates, right? Doesn't that make sense? That equilibria are functions of reaction rates. And if a reaction is changing its equilibrium, that has to be a function of how rate is changing. Yeah? So guys, understand that when you're explaining these things, yeah, you can come to this rule of thumb. You can use it as a guide. But guys, when you're explaining Le Chatelier's principle situations, it's got to come back to reaction rates and typically back to collisions. Actually, probably always back to collisions. You guys all caught up? Not yet? Some of you are actually brave enough to write down same side does the opposite, opposite side does the same, given we just said you'll never write it down. I like that. You guys okay? Can I go? Okay. So, guys, you don't need to write this down with me, but let me put in a nutshell the point that I was doing everything that I can to stress. And the point is this. Guys, this is the Haber process, right? So we've got this process, it's in a jar, it's at equilibrium. We come along and we squirt some more nitrogen into the reaction vessel. What is the reaction going to do? Well, guys, what's going to happen to the amount of NH3? It's going to go up. How do we know? Same side does the opposite. Opposite side does the same. If this goes up, that goes up. How do we encapsulate that in Le Chatelier's principle? Well, we had a system at equilibrium, and we stressed it by adding nitrogen. And this shifted the direction in order to undo the stress-causing change. So this reaction's going, hey, you added more nitrogen. I'm going to undo what you did, and I'm going to take some of this nitrogen, and I'm going to turn it into NH3, reducing the stress that you caused by adding nitrogen. And guys, what we've done now is we've created tons of misconceptions about what's going on. This reaction does not know that it's been stressed. This reaction does not know same side does the opposite, opposite side does the same. This reaction has never met Mr. Le Chatelier. He does not know, the reaction does not know that Le Chatelier has told us that reactions will respond to stress by trying to undo it. So guys, why does the reaction do this? Go ahead, Glenn. Mm-hmm. Yep. And so what changes? So the rate of the forward reaction goes up. You get it? And let's use a better word than amount, because you got to be careful with amount. It's concentration, and those are slightly different. So guys, the explanation goes like this. We increase the concentration of nitrogen. Increasing the concentration of nitrogen increases the rate of the forward reaction. As the rate of the forward reaction increases, more NH3 is produced. That's the explanation. Do you see the distinction? Now, what about this? Along the way, what's going to happen to the NH3? It's going to, well, be careful with more, it's going to go down, right? Okay, more makes me think more. So we're going to use some of that up. Well, why? Well, guys, the idea is there's more nitrogen available to collide with the hydrogens that were already there, and these are going to get, good heavens, these are going to get consumed. And so, guys, the hydrogen's going to get consumed as more NH3 is being produced, and that's all about that forward reaction rate increasing. You guys okay with the ideas? Emma, were you going to say something? I would be careful about that. It's not wrong, but that's interesting. So, guys, did you hear Emma's thought? She said, could you just say Q is less than KC? And yes, that's true. And if that makes sense to you, go with it. Because really, that's what you've done, is as you increase N2, you're taking this reaction away from its equilibrium conditions, and for it to get back there, yes. So, absolutely, you're not wrong. So if you were to put, oh, wait, no, sorry, that would not work. Sorry, I got all excited about your idea, but I'm realizing that would not. So guys, again, Emma's saying, could we just say Q is greater than KC? Here's why that wouldn't be okay. For the same reason that reactions don't know same side does the opposite, opposite side does the same, those reactions also don't know what a Q value is, right? And so while you're right that predictively, if Q is greater than KC, the reaction will tend towards products, chemistry of why it goes faster in that, or why it shifts. So yeah, I'd never heard that question before, and it's neat you're thinking about that, but it wouldn't satisfy the answer they're looking for on the test, because, and guys, you understand this fundamentally, when you're explaining things, you're always explaining the chemistry and not the ways we conceptualize it, even with Q is greater than KC. So you guys good on the ideas? Is that a good refresher? Is that all right? Okay. So guys, with that said then, here's what we're going to do. You don't need to write this down. Guys, these are the 3 ways now that you need to be able to talk about this idea of Le Chatelier's principle. How do equilibria respond by adding or removing reactants? We just talked about that, but we'll do it again. Maybe. Then what about changes in pressure? We did not talk about this last year. Guys, it turns out that gas phase, and only gas, but gas phase reactions are very sensitive to pressure changes. And it's a whole different predictive system, and we'll talk about that. And then guys, finally, temperature changes, which we did talk about last year, but I'd like to come back and refresh your memories because that's probably the one that you remember least from last year. So this is sort of our laundry list for the day. You guys good to go? Jordan, you with me? You okay? All right. So guys, here we go. So you tell me, do we need to talk about, oh, and I can't go up, poop. Oh, wait, maybe I can. Oh, yeah, look at me. Okay, so guys, this is actually a visual example of what I just did for you in blue on the board. Instead of adding N2, we're adding H2. But guys, look at the way this looks visually. So in this region, how do we know that this is at equilibrium other than the fact that it says at equilibrium? They're constant concentrations, right? This is time and concentration. So guys, we've got constant concentrations. Then at this moment in time, you open up the door, squirt in some hydrogen, and slam it closed. So you see that through this instantaneous addition of hydrogen. So we have functionally done this. We've increased the concentration of hydrogen. Now notice what happens, guys. As this thing reestablishes equilibrium, eventually over here, we reestablish that equilibrium. But guys, what happened to the amount of nitrogen before and after? Concentration went down. So as predicted, same side does the opposite. Now, what about our concentration of NH3? NH3 goes, just a second, let me roll for a second. So guys, do you see that? We started with this much NH3, we ended up with this much NH3, okay? So NH3 went up. Now guys, the thing that we haven't talked about before, but let's do it now, is look at hydrogen. We understand that initially we inserted some hydrogen, but when we reestablish equilibrium between here and here, what happened to the equilibrium concentration of hydrogen? It also went up. So guys, this did in fact go up. Now, here's the interesting question. If we could calculate Kc here, and if we could calculate Kc here, what would they be? The same. So, guys, understand that changing concentrations does not change the value for Kc. But relative to before and after the change, this is where Le Chatelier's principle helps us. When it establishes the new equilibrium, this is lower and this is higher, but it's at the same Kc. Why would Kc not change? What is Kc dependent upon? Go ahead, Emma. It's and they settle back in, right? But why couldn't they settle back into a different ratio? The little k stay the same, right? Because remember, we've said that all along. Big K is equal to the ratio of little k forward divided by little k reverse. And guys, if we back this all the way out, rate is equal to little k times concentrations. And that's functionally what we're doing. We're changing the rate, in this case of the forward reaction, not by changing little k, but by changing a concentration. That's why the rate accelerates, as Gwen got us thinking, The rate in the forward direction is accelerating because we're adding hydrogen, more collisions. That does make the forward rate go faster, but it's not adjusting the value of the rate constant, and the value for Kc hinges on the rate constants, and so the Kc's don't change. Is that okay? All right, so guys, this is what you need to know about those concentration relationships, things you want to talk about. Brendan, I thought you might have had a question a second ago. You okay? Okay, go ahead, Matt.
So the gap between H2 and NH3, so it's like the difference in concentration.
Hold on, maybe if I clean up my mess. Okay, so start again.
The height difference between H2 and NH3, so say it's like the difference in the concentration if like hydrogen was like 2 molarities, say.
Okay.
And then NH3 is a gas.
Keep going. I think I know where you're going, though.
Is it the same, like, difference?
Right. So can I draw?
And after?
Like, is this height equivalent to that height?
Or is that height the same on the when equilibrium is reestablished?
Right. And the answer is no. Let me see if I can do this. So maybe we could even bring this into the conversation and say, is there a relationship between the amounts that some of these go up and the other go down?
Yeah.
And there is a relationship. And that's the problem. The relationship is complicated by the fact that these are exponents. If this balanced with all ones, then the changes in the heights, if you will, which are representative of concentration change, if this balanced with all ones, then these changes in height would in fact be linear, directly proportional. But linear, right, because it's all ones. Here, that's not the case because of these exponential factors. But if we could account for the exponential factors, but that would take logarithms, we would find that there is a linearity to it if we were to get rid of the exponential forms. So, and you could do that with logs, but I'm not nearly that good at math. So, you guys good with concentration stuff? Okay. All right, so guys, now let's move along and let's look at the next thing we need to talk about, which is changes in pressure. And this is new. This you got to get in your notes. Now again, guys, remember, we're going to talk about this predictively, but predictively is different from splaining. When you splain, you got to talk when you explain, you've got to talk about chemistry, rates, and collisions. But let's talk about it predictively first. Oh golly, why did that happen? That was weird. How did I do that? Oh, hold on. Oh, now it doesn't work. I am. If I click on the right side, it goes back. I have no idea, but I just like that I have that as an option now that my little baby keyboard's dead. Okay, so guys, it goes like this. And important thought, pressure has to be gas equilibrium. So if you have a gas phase, gaseous system, and it's at equilibrium, and the volume is increased, which, thank you, Boyles Law, tells us the pressure will go down. Right? Boyles Law, the indirect relationship between pressure and volume. If you have a gas phase system and it's at equilibrium and the volume is decreased, so the volume, it gets smaller. And if you take a gas and make it smaller, its pressure goes up. The reaction will shift towards the side which has the fewest moles of gas. Yeah, interesting, right? So guys, a convenient time to come back to the Haber process, because that is a gas phase process. So maybe we could include that in our notes. And then let's talk about this. Let's talk about how we think about this. Let's talk about fundamentally why this works. Thank you, Avogadro's principle. And then let's talk about how to explain it given collisions in chemistry, reactions. So, guys, predictively, all of this, are you caught? Wait, sorry. I get all excited. No, but I could show you a picture of the thing that my son's date gave him on the porch. I have pictures of that. No, it won't. But you know what, Brandon, it's interesting. It's funny you asked that question, do I have pictures? Because frankly, as I started thinking about this, the thing that I immediately did is pictures started to pop into my mind. And my pictures were pictures of those stupid circles that we drew on the board during the gas unit, where I was mentally, just a second, Ash, I was mentally drawing a circle in my head and putting gas molecules in it. So maybe together we could try to make up some pictures. I haven't done that. Let's talk concepts and then see if as a group we can come up with pictures. Go ahead, Ashley. Really? So, I have to be honest with you, those pictures don't look anything like the pictures that came up in my brain. Does that make sense to you? Really? So let's do this. Guys, if you would allow me, turn the page. Let's turn over to page 636. Not because there's anything valuable on page 636, but because I know you'll be incapable of paying attention if you've got a picture in front of you. Because you're going to be trying to figure out the picture rather than trying to understand the concept. So what I'd like to do, if you'd allow me the freedom, is to talk about this. Talk about this predictively. Then maybe we draw pictures, and I love that. Actually, I look at that and it doesn't make sense to me. But let's do this. Let's get everybody to the point where we can talk about this predictively, and then maybe we go, let's go back to 636 and say, okay, now that we understand the concept, let's look at the picture. I told you, you can't help yourself. Oh, you didn't go back there. So guys, let's then go back and go, does this picture make sense? And if not, what makes more sense? Okay, so guys, in order to do this predictively, here's the first thing that you've got to do. How many, and this is right, all of Le Chatelier's principle comes down to the balance between reactants and products. So guys, looking at the reactants, how many total moles of reactant gas are represented on the board? 4. We've got 4 moles of total gas. 1 mole of nitrogen, 3 moles of hydrogen. Okay? How many total moles of product gas do we have? 2. Okay. Now, guys, for argument's sake, just to bring this back to something that's going to feel familiar, let's pretend that this is at standard temperature and pressure. What is the volume of 1 mole of gas at standard temperature and pressure? Do you remember? 22.4 liters. Remember that number? Okay. So, guys, let's pretend the 0.4 doesn't exist and let's call it 22. So if a mole of gas has a volume of 22 liters at STP, how big is 4 moles of gas? 88 liters. Does that make sense? Okay, so assuming this reaction is at standard temperature and pressure, how big is 4 moles of gas? 88 liters. So guys, how big is 2 moles of gas? 44 liters. So now, guys, we've got a problem. Law of conservation of mass. What does the law of conservation of mass say? Matter can't be created or destroyed. So, guys, how many atoms of nitrogen are going in? 2. How many are coming out? 2. How many atoms of hydrogen are going in? 6. How many atoms of hydrogen are coming out? 6. So, guys, how can this be? Let me set the stage. This reaction does not violate the law of conservation of mass. Everything that's going in is coming out. But when it comes out, the size cuts down in half. But it's the same amount of stuff. How can that be? Yeah. Exactly. Guys, that's Avogadro's principle, right? It doesn't matter what the molecules are, because gases don't fill spaces like this, right? Gases fill spaces like this. And as a result, it doesn't matter if it's nitrogen, hydrogen, or NH3. The volume they occupy can be smaller for the same amount of matter, because again, Avogadro's principle says it doesn't matter how big the molecules are because of all the free space around them. So guys, functionally, this is what that means. Does this keep in holding with the law of conservation of mass? You bet. But there's no such thing as a law of conservation of volume. Do you see what we're saying? So guys, over here, these 4 moles of gas take up 88 liters. Over here, the exact same amount of stuff is now contained in half the space. How can that be? Because now all of these small molecules got bound up in bigger molecules, but because the size of the molecules themselves really doesn't matter, physically it gets smaller. Do you understand the idea? Okay, now let's talk about how this thing responds to pressure. So say that we take, can you picture this? We've got our balloon, and in here we've got some N2s, we've got some H2s, we've got some NH3s, and they all came to equilibrium, and then we take that thing and we squeeze it, and we put it in a small container. How is the equilibrium going to respond? It's going to go in this direction. This is going to go up. Why does that go up? Because it's small. Just for now. We'll explain it better later. But for now, guys, the idea is this. So we've got 4 moles of gas over here. We've got 2 moles of gas over here. Which is bigger, 4 moles or 2 moles? 4 moles. So if you take a gas and you it, stress. So how does the reaction respond to that stress? Well, it goes, hey, if I've got less space than I can occupy, then I'm going to be happier if I'm smaller, right? I mean, there's evolutionary things that do this, like animals that are trapped on small islands. I don't know if you know about this stuff, but guys, they found these islands in the middle of the Pacific. Who knows how they got there, but there are these monkeys on these islands, and they are genetically identical to these monkeys that exist on the mainland, but they're smaller. Why are they smaller? Because their environment is smaller. Small things tend to do better in small spaces. Big things tend to be okay in big spaces. Don't take the analogy too far, but the same thing's going on here. Guys, if you take a system and put it in a smaller space, increasing the pressure, that system is going to respond by trying to get smaller because that reduces stress. Do you understand the concept? But you also understand you'll never explain it that way, right? So now let's talk about why. So guys, do this. Let's talk about what happens when we have, this is our small space. This is now our small space, and we're going to talk about the reactants and products separately. So in this small space, good heavens. Guys, in this small space, here's what we've got. Looking at ratios, in this small space, we've got that. And then if we were all product, in this small space, we're going to do this. Now, guys, think about this. You've got the gas in the big space, and it's at equilibrium, right? So that means the reactants are colliding together and forming products. The products are colliding together and forming reactants. Now, when you put them in a smaller space, what's going to happen to the frequency of those collisions? It's going to go up for everybody, right? If you take a gas and put it in a smaller space, everybody's going to be colliding more. But they don't collide more equally. why would these in a smaller space collide even more than these? There's more particles. Do you get the idea? So when you take these gases and put them in smaller spaces, functionally increasing their pressure, their concentration, the idea is this responds more. And the reason it responds more is because there's physically more of those particles. So when you take a gas equilibrium and put it in a smaller space, the side of the equilibrium that contains more particles will have a disproportionate increase in rate because there's physically more particles there. Does that make sense? Questions about that? Go ahead.
When it comes to the reverse reaction, does it just like spontaneously decompose?
They do, and that's actually what happens. And so the idea, let's talk about it. So what then happens, forgive me, but what then happens if we do the opposite and if we put these in bigger spaces? So now we've got N2 and we've got 3 H2s. This one's a little harder to understand, but I think I've got a way that might work to explain it. So guys, what's going to happen to this if we put it in a bigger space? Decreasing the pressure. What's going to happen? Which way will the equilibrium shift? To the left. Does that make sense? So similar logic, if you put something in a small space, it'll shift towards the side with fewer particles. If you put something in a bigger space, it'll shift towards the side with more particles. How do we explain it though? Yeah, and that's it. We've got to talk about it relative to collisions. So guys, when you spread it out, what's going to happen? Well, all the collisions are going to slow down, right? But will they slow down equally?
Because the forward reaction relies on collisions, there's less collisions, but the reverse one just happens regardless of how the collision.
Because it's a decomposition.
Yeah.
Right.
So it'll just happen, and so the
Right. Right. And so that's the explanation. But with that said, let me just tell you this. That's hard to explain, right? And that's the way I think about it, rather than thinking I get it. When something's compressed, the side where there's more particles to collide, the rate goes up disproportionately and that goes faster. The reverse process is harder to explain. The way that I think about it is the reverse reaction slowing down less. Do you know what I'm saying?
yeah.
I've never seen on an AP test, though, where they've had you go through that thought process simply because it is so hard to explain. So with gas phase reactions, here's what you're going to see. They will either say, you've got a gas phase equilibrium and you put it in a bigger container, which direction will the equilibrium shift? And then you could just say, in this case, to the left. But that would be in multiple choice where you can't explain it. Or they would give you questions where it's only shifting towards the side that's got more particles with an increase, or less particles with an increase in pressure. I've never seen on an AP test where in free response they've had you guys explain why an increase in volume would create a shift in equilibrium. It's tough to explain. You guys okay with the idea? Okay. So now, Ashley, let's do it. Help me understand this picture because I don't get it. What is that picture? Okay, so looking at the top of 634, and I wish I could put this on the screen, but I can't. So we've got 2A in equilibrium with B. So there's a greater amount. So you've got 2 moles of A, 1 mole of B. So if we go to the right, which is an increase in volume and a decrease in pressure, we'll get more A, right? And maybe I'm trying to get something that, right, I'm wondering if that, I was hoping for an explanation. This is more just a visualization. Do you see explanation in that? Right.
You can say that A
Right.
is part of
Yeah. But I agree with, and I'm not trying to argue with you, obviously, but I see it now. I see it as in a visualization sense, but I don't see it as in an explanation sense. Yeah. And then similarly, if we go to the left, smaller, that would favor B, and then so there would be more B. So guys, is there a way that we could redraw or draw something different that would provide explanation?
On the arrows, to show how like two red circles go together to make a gold, and then you get more golds than reds.
Oh yeah, and then on the right way.
A gold turning into two reds.
Interesting. That's a neat idea. Does that? Yeah, that's interesting. That's a great idea, Matt. I like that visualization. What do y'all think? You guys okay with pressures? Yeah, okay. But again, we're in agreement here that we've got to be able to explain it relative to collisions, right? And not this idea of big gases are happier in big spaces. Although that is true, but we're not going to say it that way. Yeah.
So is it just in this case we mentioned how the H3 just decomposes faster than the collisions?
Yeah, and honestly, Austin, I was just about to mention this when Matt was helping us visualize this by two reds becoming a gold and a gold breaking apart into two reds. It doesn't just work then. I like the explanation that we've arrived at for why gases get bigger in bigger spaces. And relative to decompositions, it makes logical sense, right? But it turns out that it doesn't just work for examples where the reverse reaction is a decomposition. The logic works even in places where the reverse process is collision-based, is bi and termolecular, and not just where it's unimolecular in a decomposition. It actually works there too. And frankly, my brain is spinning in the background trying to explain it. But I chose not to do that because they'll never ask you that on the test. And I think we found a comfortable place to be given Matt's explanation of things spontaneously falling apart. But it does in fact work when this reverse reaction is collision-based. But to try to explain it is something we'd never be asked to do. So I think we could just leave it alone.
It just knows the pressure.
Exactly. Then it is actually a question of happiness. Yeah. So Austin, I know that's not terribly satisfying. But to be honest with you, I mean, maybe if we stood here long enough, we could figure out a good way to explain it, and it might be fun to do at some point, but I don't think it's a good use of our time right now. Yeah, go ahead.
So, on the textbook questions, what are some examples of questions?
Yeah, so relative to gas phase equilibria, you'll see them in multiple choice. And then it's typically questions like, you've got the Haber process, you double the pressure, which direction does the equilibrium shift? And guys, understand, we should say this. When on the AP test, when they're talking with you about Le Chatelier's principal questions, the phrasing, if you will, they will ask you to talk about shift right and shift left, or shift towards products and shift towards reactants. So for example, say that this is a concentration equilibrium. So if this goes up by concentration, same side does the opposite, opposite side does the same, right? The way that you would communicate that on the AP test is the equilibrium shifts to the right, because that's the one that goes up. It makes more of this. So the equilibrium is shifting towards the side where more is produced. So in multiple choice, the question would be something like, you have the Haber process, you double the pressure, what direction does the equilibrium shift? Do you know what I'm saying? The answer would be to the right, because 4 and 2 is smaller than 4. Relative to free response, they could ask you the same kind of questions. They may ask you to explain it, and then it comes back to a collision-based explanation. And rates. You stretching? You guys good? Are we okay? Okay. So guys, the last one we need to then talk about is temperature. So, oh, that doesn't work. Okay, so we did that. We're good there. So guys, temperature. So guys, here's the thing that's interesting. When we change concentration or pressure, oh, that was a bigger drink than I thought. Okay, so guys, when we change concentration and pressure relative to Le Chatelier's principle, as we established on the very first slide, that doesn't change Kc or Kp, right? And again, if you want to connect the dots, the thought was Kc is dependent upon little k's, and because we're not changing little k's, we're not changing Kc or Kp, right? Collisions, rates, okay. Well, guys, this then should not come as a surprise that when we change the temperature, it changes the equilibrium by changing Kc. The equilibrium mixture doesn't look the same. But guys, you can take that sort of as an interesting little factoid. The important stuff that you need to be able, and does that make sense? Maybe we should pause there because you're going, wait, if it was important enough to talk about, we should at least try to understand it. So does that ring okay with you? That when we change pressure or concentration, the reactions, as we saw in that Haber process thing when Matt was talking about elevation changes, to refresh your memory, because we saw that when it reestablishes equilibrium, it comes to the same ratio as Emma got us thinking. It's at the same ratio. But guys, when we change temperature, the ratio changes. Because, remember, little k is dependent upon temperature. Are we okay? I don't want to belabor something that you're okay with. Are we good? Okay. So, but guys, what you've got to be able to do is you've got to be able to do this predictively. And this is the way that you do it. When you do this predictively, the easiest thing to do is to think about heat, right? Changing temperature, heat. Think of it as a reactant or a product. So if you've got a system that is exothermic, negative delta H, going back to chapter 5, negative delta H, think of heat as a product, because it really kind of is. It's being produced. And then, guys, similarly, if you've got a reaction that is endothermic, heat is coming in. Think of it as a reactant. And then, guys, with that as a backdrop, you can then use same side as the opposite side is the same, in order to figure out the changes to the equilibrium mixture. Uh-oh. Are you guys caught up? Okay, I want to show you this relative to the Haber process, but I frankly don't remember if the Haber process is endo or exothermic. Have you guys seen anything in the book what are the chances Siri knows? Is the Haber process endo? I hate Siri. Yeah, interesting question, Zach. I haven't asked you a question. Is the Haber process endo or exothermic? Haber process. You're going endo? I think it actually is endothermic because if I remember correctly, what Haber figured out to do to maximize the yield, oh no, it's exothermic. Yeah, it's exothermic on the order of negative 92 kilojoules per mole.
But it's like, so is it spontaneous?
Oh yeah, because exothermic tends towards spontaneity.
Yeah.
But okay, so guys, we've got this. We've got N2 plus 3H2 in equilibrium with 2NH3, and the delta H is on the order of negative 92 kilojoules per mole. So endo or exothermic? Exothermic. So guys, we've identified that this is exothermic. So what we're going to do with that information, NH3, so we're going to make heat a product. Does that make sense? If it's exothermic, it's giving off heat. Let's treat it as a product. And as soon as we do that, we can now apply the same side does the opposite side does the same logic to how this would shift equilibrium. So guys, what does that then mean? Well, if we take the Haber process in a bucket and we heat it up, I'm not even going to draw, let me just ask you. If we take the Haber process at equilibrium and heat it, which direction will that push the equilibrium? To the left, towards the reactants, towards the left. The thought being this, that if we increase heat, then that will make this go down and these go up. Thank you, Le Chatelier. That means the equilibrium shifts in the left. Now, how do we explain that at a chemical level? And guys, frankly, they wouldn't ask you to do that. The reason is because what's really happening is we have a K forward and a K reverse. And for reasons that we don't need to get into, this reaction is actually, so the reverse process is actually more temperature dependent than the forward process, and so heating this would cause a greater amplitude in the reverse rate than it would in the forward rate. Both will be speeding up because all reactions speed up with an increase in temperature. It just so happens that this reverse reaction is more temperature dependent, and so consequently the reverse reaction will accelerate more. That said, you don't need to be able to talk through that. You just need to be able to say that it'll shift to the left.
So all equilibrium processes by definition have to be spontaneous in both directions, right?
Well, be careful because the answer is technically no. We learned in chapter 5, the definition of equilibrium is a reverse, and this isn't word games, this is important. The definition of a reversible reaction is a reaction. Let me start again. The definition of equilibrium is a reversible reaction. And so what does it mean to be reversible? That means spontaneous in both directions. And what that then means is that the forward and reverse reactions are undoing each other with no net change in Gibbs free energy. Enthalpy and entropy together are not changing. Right, so when we say that this reaction has a negative 92 kilojoule per mole delta H, that's going towards equilibrium, not at equilibrium, because at equilibrium, energy out and energy in are the same by definition because it's at equilibrium.
Yeah, so I was just wondering, so it's exothermic, and then heat causes ammonia to decompose, right? So would that be what's causing it?
Well, you have to be careful because heat causes this to decompose, but heat also causes these to react faster. All reactions speed up with increased temperature. The difference is that the reverse process speeds up more. Okay, why? We don't need to talk about it. So what do you have to be able to do? All you've got to be able to do is say, if heat goes up, this goes down, those go up, same side does the opposite side does the same, that shifts the equilibrium to the left. But understand again that increasing the temperature speeds up both reactions, forward and reverse. So it's not, you can't say this favors reactants because increasing the temperature causes the rate of the NH3 decomposition to go up. While that's true, it causes this to go faster too. It doesn't explain the phenomenon. Is that okay?
So you could stop the heat from escaping and remain the exact same.
And that's equilibrium. Heat in is heat out. Yep. You guys good? Okay. So guys, one more to talk about. This turned into a bigger day. This has been enjoyable. So guys, the last thing is this. What about catalysts? So guys, here's the thing that's interesting to me. But you know I'm fascinated or probably intimidated by catalysts. So guys, what happens when you add a catalyst to an equilibrium system? Because guys, we understand that catalysts change the value of little k, right? Right? Okay, so catalysts change the value of little k. What we haven't done is talked about how do catalysts change the value of little k for a forward compared to a reverse reaction at equilibrium. And here's the thing that's interesting. Because catalysts, and I know you're right, I shouldn't have even brought this up. Guys, because, I know it's okay, you guys, I forget, you can't help yourselves. So, guys, but here's the idea. Because catalysts create a new pathway, catalysts actually have a proportional change on both the forward and the reverse processes. Consequently, catalysts do not change the equilibrium. What they do is allow the reaction to come to equilibrium faster. Isn't that interesting? And it's all because a catalyst creates a new pathway. And that pathway is new for both the forward and the reverse reaction. Consequently, they're coming to the same products and reactants in the reverse direction. They just get there faster. So the idea then is this. Catalysts do change the rate of the reaction, and they do that by decreasing the equilibrium or decreasing the activation energy. But guys, this decrease is equal for the forward and reverse processes. As a result, they get to equilibrium more quickly, but Kc doesn't change. So you will not be asked the question, if you add a catalyst to this reaction, does it shift to the left or the right? The answer is neither. Ooh, they could ask you that.
So the concentrations won't change?
No, nothing changes. Nope. It just gets there faster. Yep. So guys, are you caught up with me? This is a little thing we like to call homework. Do you guys love how Isabel just takes this in and